Hello students, welcome. In this video we will discuss electric field due to a line charge or electric field due to a thin infinitely long straight wire using Gauss theorem. So first of all, let us suppose we are having a infinitely long straight line charge like this one. This be the infinitely long straight wire like this one, y dash. So you know the electric field due to this positive charge distribution will be radially outward, and suppose you are interested to find the electric field at point P lies at a distance r from the linear charge distribution. You can take this point P here or here, no any problem, right? So now just write, let a thin infinitely long straight line charge having a uniform linear charge density lambda. We have already studied about the linear charge density, surface charge density, and volume charge density. So to find the electric field at point P, draw a cylindrical surface of radius r and a length L. How? So in the radiuses are so in this way you draw a cylinder of radius r and let its length be L. This is the positive charge distribution, so direction of electric field you know, radially outward, and be represented by E vector. So we are interested to find the electric field at point P, so draw a small area ds here, and you know the area vector. Area vector is a vector perpendicular to this area, so it will lie in the same direction of electric field. Now you divide it in three parts. Let this be your first part, this is the second part, and this is the third part. So first of all, write to find the electric field at point P, draw a cylindrical surface. जो असी ड्रा किया है, draw a cylindrical surface of radius r and length L. This cylindrical surface is called as the Gaussian surface. And you know the Gaussian surface, a surface where electric field over each and every point will remain the same. Now electric flux phi is equal to, what is electric flux? Electric flux you know it is the dot product of electric field and area vector. So it is equal to E dot ds for the first part plus second part plus third part, because we have divided it in three parts. This curved part be part 1, then this circles in part 2 and 3. Now if you see here, the direction of electric field for part 1, it goes perpendicularly like this one. But if you see here, the direction of electric field goes in this way, right? Means electric lines of force are going parallel to the end faces. End faces mean this face, our part 2nd and our part 3. So here for part 2 and 3, electric field is parallel to end faces. Electric field is parallel to end faces. If electric field is parallel, right, so electric flux will be 0. Means to say, here in this phase and in this phase, electric flux will be 0. So now the electric flux for the first part will be only E dot ds. If you see here, in the curved part, electric field is not parallel, but it is perpendicular to the surface, right? Perpendicular to surface but parallel to area vector. This is the important point. See here, electric field is perpendicular to this surface, right? But area vector also lies in the same direction. So electric field and area vector are in the same direction. So here angle will be 0. But if you see in this case here, electric field go parallel to the face, right? So electric field is going parallel, right? But whenever you will take the area vector, it will be perpendicular. So angle between electric field and area vector will be 90 degree. So EDS cos 90 will be 0. So here it is EDS cos of 0, that is EDS. Cos 0 is 1. So E into integral of ds. But is now integral of ds? Integration of ds. When we will integrate this small area, we will get the total curved area of this cylinder. So curved area of cylinder is 2 pi RL. So in this way, this is our first equation, and in this equation we have calculated the electric flux through its definition. Now, according to Gauss theorem, but it say electric flux is equal to 1 over epsilon 0 charge inside. So charge inside will be Q. So Q upon epsilon 0. Also, we have taken the linear charge density, that is lambda, and that is what? Charge per unit length. So Q from here, Q equal to lambda into L. It will be multiply here. Q into lambda. So your Gauss theorem comes to be lambda L over epsilon 0. This is the second equation. Now this is electric flux from the definition we have calculated, and this is electric flux from the Gaussian surface, Gaussian theorem. So now equate both these equations. Left sides are equal, so right side will be equal. So E into 2 pi RL equal to lambda L over epsilon 0. So E equal to 1 upon 2 pi RL into lambda L upon epsilon 0. So L will cancelled out and you will left only with 2 pi R epsilon 0, or you can write it in simple way, 1 upon 2 pi epsilon 0 lambda upon R. So this is the electric field due to the line charge or due to a thin infinitely long straight wire. So in the next video we will discuss electric field due to the infinitely plane sheet of charge. So thank you for watching.